In the last section, we looked at long-run behavior of polynomials, and in this section, we're going to look at the short-run behavior of polynomials. So just for a little background, let me bring up Desmos here, and there we go. We have Desmos up, and I'm looking at 3 different polynomials. All right, they all have a leading term of x to the 4th, but the rest of the function is different. Okay, so in the long run, they're going to this polynomial, all of these polynomials are going to be dominated by x to the 4th. And so if you look at the long run behavior of all 3 of these polynomials, they all look very similar, right? They're going off to infinity in both when x goes to positive infinity or when x goes to negative infinity. So it's hard to really tell them apart just by looking at the long run behavior. But if I zoom in closer, so I'm going to, let's see, I'm going to change the scale on the y-axis here. So I'm going to make it maybe minus 10 to 10. I don't know if that's what I need to do. Now you can see, now that actually might be, let's do minus 40. All right, let's do that. And let's make this 20. All right, now that's probably a good scale. All right, so now you can say, oh boy, they look very different in the short run, right? When we're talking about short run behavior, we're talking about the behavior closer to 0. All right. Now, sometimes people will say it's close to the origin, but I mean, we could be looking at, it's all relative to infinity. So it's closer to the origin. All right, so now you can see these functions have very, very different behavior. If I turn off some of these functions, let's turn off those functions. Now you can see the first function looks like that. If I turn that one on and turn this one on, the next function looks like that. And I'll turn that one on and turn this one off, on and off. Right, then they look very, very different in the short run. Okay, so that's the idea here, is we're looking at the behavior of these polynomials in the short run. So closer to the origin than infinity, so which is sort of relative. All right. So in general, with short run behavior, we're looking at where does the polynomial cross the horizontal and vertical axes. We're also looking at the value, whether the value of the polynomial is positive or negative, right? So if the graph goes above or below the x-axis. Now, just a little bit of vocabulary. The places where the function crosses the horizontal axis are called the zeros of the function. They're the places where the value of the function is 0. Okay, that's the place where they cross the x-axis. All right, they're called the zeros of the function. And in order to determine the zeros and the short-run behavior of a polynomial, we need to factor it. So let's take a look at the first example here. We have f of x is equal to x cubed minus 4x squared plus 3x. So the first step here is just to write f of x as the product of linear factors. All right, so I'm just going to factor this polynomial as much as I can. All right, so I'm seeing, first of all, that there's a common factor of x in every single term. So I'm going to factor out an x. And then I'll get x squared minus 4x plus 3. Now I have a quadratic that I can factor. And so I'm looking for factors of 3 that add to negative 4. So if I look at x minus 1 and x minus 3, okay, that will multiply out. X minus 1 times x minus 3 will give me that quadratic. All right, so now I have the function in factored form. And now I want to find the zeros of the function. All right, so what I'm going to do is I'm going to look at where is f of x equal to 0. And f of x is this in factored form. And so I can see that when x is equal to 0, the whole function will be 0, right? Because I got one factor that's 0. If x is equal to 1, right, 1 minus x will be 0, so that factor is 0. The whole function will be 0. And then finally 3. So f of x equals 0 for these 3 values of x. And so that is where f of x crosses the x-axis, right? And if I want to list the points as ordered pairs, it would be 0, 0, and 1, 0, and 3, 0, right? The y value is always 0, and these are the x values that make f of x 0. Where does the function cross the y-axis? Right? It's going to cross the y-axis when x is equal to 0. Oops, x is equal to 0. All right, so all I need to do there is just evaluate f of 0. And if I put 0 into either the factored form or the original polynomial, I'm going to get 0, right? So we can say that f of x crosses the y-axis at 0, 0. All right, now we get into the nitty-gritty here. We want to know where f of x is positive and where it's negative. All right, now the way I like to do it is to look at each factor. We have 3 factors in this. Maybe I should scroll up just a hair so you can actually see the function. And so we have 3 factors in the factored form, and the sign of those factors is going to determine the sign of the overall function. So one way to look at it is just to look at the factors x and x minus 1 and x minus 3, and then we can look at the product of the sign of each one of those factors to determine the sign of f of x. All right. Now it's going to be different in different intervals. So I'm going to just make a little table here. All right, I'm just going to make a little table, and I'm going to divide the domain into intervals, and the intervals are going to be determined by the x-intercepts, right? The place where the zeros of the function, the places where the function crosses the x-axis. All right, so I know that it crosses the x-axis at 0, 0. Or it touches at least the x-axis at 0, 0, 1, 0, and 3, 0. And I know that the only place where it could possibly go from negative to positive is where it crosses the x-axis, right? It has to cross the x-axis if it's transitioning from negative to positive or positive to negative. So that's what I'm just going to break the domain into 4 intervals. I'm going to look at x less than 0. I'm going to look at x between 0 and 1. I'm going to look at x between 1 and 3, and then finally x greater than 3. So I've just broken the domain into 4 different intervals, and I'm going to look at the sign of each one of the factors in that interval. All right, so if x is less than 0, it's negative, right? So then x is negative, right? And I can actually just evaluate this all the way down. If here, anything that's greater than 0 is positive, so x is going to be positive, 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 all right? Let's look at the next factor. If x is less than 0, this taking something negative and subtracting 1, it's going to be negative, all right? Between 0 and 1, all right, I'm taking something that's less than 1 and I'm subtracting 1, I'm going to get a negative. And then if it's greater than 1, then I'm going to get positive. All right, next factor, I'm going to look at if x is negative and I subtract 3, it's going to still be negative. If x is between 0 and 1 and I subtract 3, it's going to be negative. If it's between 1 and 3, right, 2.5 or something, or 2, I'm still going to get a negative value for that factor. And then if x is greater than 3, then finally it's positive. Now, in order to determine the sign of the overall function, I'm just going to multiply the 3 factors. So if I take negative times negative times negative, it's going to give me a negative. positive times negative, right? I got negative times negative is positive, and then I'm taking times positive, so it's just going to be positive. Positive times negative is going to be negative. Positive times positive gives me positive. So now I have the sign of the overall function, and if I want to sketch a graph, all right, so I'm going to this is just a sketch, all right. So I'm not even going to worry about what the y values are. I'm just going to look at, I'm going to first of all put in the zeros, right? So here's 0, 0. Let's say this is 1, and this is 2, and this is 3. All right, 1, 2, 3. I'm only going to number the x-axis. I'm not going to really worry about what the values of the function are. I'm just trying to figure out where it's positive and where it's negative. All right. So if x is less than 0, it's negative, right? So it's going to be this way, right? It's going to be this way. Now, between 0 and 1, oops, I better draw in all of my zeros, right? So I have a 0 there and I have a 0 there. Between 0 and 1, it's positive, right? But it goes up and it comes back down to 1, right? So there's you know, it has to turn around at some point in order to come back to 0. But it goes positive, and then between 1 and 3, it's negative. All right, so it's going to go something like this because it has to come back to 1, and then when x is greater than 3, it's going to be positive. All right, so that's just a general shape of the function. So this is what the short one behavior would look like. So now, just another little bit of vocabulary here is the turning point. A turning point is where the graph changes from increasing to decreasing or decreasing to increasing. So you can see we have a turning point right here. This would be a turning point. That's what we call it. Oops. Turning point, not a tuning point. That's a turning point because you can see it went from increasing to decreasing. This down here would also be a turning point because we went from decreasing to increasing. All right. And we know there's got to be a turning point. We don't know the exact value of where that turning point is happening at this point. But we know there has to be some sort of turning point between 0 and 1 because it's got to come, it's positive, and it has to come back to 0, right? So it's getting more and more positive, but at 1 it has to be coming back to 0, right? And we know that a polynomial I know that a polynomial is a continuous function, and so it's not going to have like some weird asymptote or something in the middle, some weird discontinuity. All right, so there we go. That's the first example, and I'll meet you in the next video for the next example.